Welcome back to another video looking at another important chemistry concept in the HSC chemistry course, which is natural ozone reactions. So you probably watched the videos before where we looked at ozone and the structure of ozone and the layers of the atmosphere, and that we know that ozone is an important upper UV radiation shield because it absorbs incoming UV radiation. So let's look a little bit more about that and the natural ozone reactions, the formation of ozone in the stratosphere and the destruction of ozone in the stratosphere. So to understand this concept properly, I guess we really have to sort of take our minds back to the EM spectrum. Okay, so if I'm zoning in here on the EM spectrum, and this is, we'll just say, call this the end of the visible region, right? So this is the visible region. And the visible region, remember, had red, orange, yellow, green, blue, indigo, and violet. And so this is the ultraviolet. Okay, so this is the ultraviolet going that way. And then, of course, we can go on to, after ultraviolet, X-rays, gamma rays, cosmic rays. So if we just say for the moment that this is UV radiation, you can see that there's different intensities of UV radiation due to the frequency and the wavelength. So if we break this up into three regions, so if we look at the different areas here, we can see we've got UVA, UVB and UVC. UVA has a wavelength around about 320 to 400 nanometers in length. Then we have the next region here, UVB, which is 290 to 320. And then we have UVC, which has the smallest wavelength and therefore the greatest intensity of 100 to 290. So you can see here that as we're moving towards the right and getting closer to gamma rays, the wavelength decreases, and therefore the intensity or the penetrating power of our UV rays goes up. And so UVC, which is the most damaging, then we have UVB and then UVA. Now UVA penetrates the most in terms of to the surface of the Earth. So we have high penetration to the surface. Right, high penetration of the atmosphere. Then we have UVB. Now some of the UVB reaches the atmosphere, but most of it is blocked by the UV ozone. I should say the UV radiation shield, otherwise known as ozone. So if we do that, then we've got ozone molecules here. Okay, so most of it is blocked, only some gets through, and then UVC, none gets through. All right, so that's just sort of trying to show you visually that UV radiation is blocked by the ozone, but specifically completely blocked UVC, a little bit of UVB, and UVA goes through. And it's these ones here that are most damaging. They're the ones that do the most damaging to cancer-causing agents in our skin. They can, they result in melanomas, etc. So they have the most biological effects. So what we're going to do is look at now some of the reactions that go on to form the ozone that we have in the stratosphere. All right, what we're going to be looking at now is the natural formation of ozone in the stratosphere. And so what happens here, we've got oxygen atoms up there, or I should say oxygen molecules, sorry. Then what happens there is the UVC radiation comes along and breaks that oxygen bond. And we've talked about this before, where it's a homolytic lysis. In other words, it's broken evenly, and the electrons go to make two radicals. Okay, so we have an oxygen radical here and we have two of them. Now those radicals are very, very reactive because they've got an unpaired electron, right? And so then what happens then, another oxygen molecule reacts with the radical, I should say the radical reacts with the oxygen, and that makes ozone. Now that ozone, I'll put a little asterisk there, is sometimes called metastable, or it's unstable, right? So we'll just say that there equals unstable. In other words, it's got a lot of kinetic energy, right? It's got a lot of vibrational kinetic energy because of that extra energy that it's occurred due to the formation of this with this radical. Now that can decompose, but to prevent it from decomposing, if this molecule here of ozone collides with other adjacent molecules, usually oxygen, right, or nitrogen, then that energy is dissipated or given off to the kinetic energy of those molecules, and this becomes more stable. Okay, so We have the formation of the radicals. The radicals react with oxygen to form a metastable or highly reactive kinetic energy molecule of ozone that then can collide with adjacent oxygen and nitrogen atoms. It loses that extra energy and becomes more stable. Okay. Another thing it can do is sometimes it can release that extra energy due to a photon. So it can release it as a bit of energy or a photon of light. Right. I'll just put HF there. Right, because the energy of a photon is the frequency times Planck's constant. We'll just put HF there. So it can release it in those forms there. So that's the normal formation of ozone, and that happens in the stratosphere. Now what we're going to do is rub all this off, and we're going to look at the natural destruction, because ozone, of course, can be destroyed naturally, and we have this continual cycle, this natural cycle of making it, destroying it, making it and destroying it. And on average, we have a layer, a thin layer, I think it's about 3 millimeters or something. It's not very thick, but it's a thin layer of ozone that protects us for incoming radiation. So let's look at the destruction cycle. All right, now for some natural destruction of ozone. So in the stratosphere, we get the absorption by ozone, UVC radiation, right? So here we have UVC. That gets absorbed by the ozone to produce an oxygen plus an oxygen radical. Now remember, you probably noticed in the previous video, I just corrected what I said before, going from the oxygen forming ozone. It just absorbs general UV, not UVC. This absorbs UVC. So the bonds in ozone energetically absorb UVC. So what we've got here is we've got now a breakdown where we have oxygen and an oxygen radical. Now what happens is that oxygen radical can react with other ozone molecules. In fact, 25% of the oxygen radicals will react with further ozone molecules. And when that happens, we get breakdown to oxygen. Okay, but there is a problem, because we've still got a lot of other breakdown happening due to something else. And the other something else, the 75%, is due to radicals. Right? So radicals could be hydroxide radicals, they could be nitric oxide radicals, etc. Okay, so these radicals in the air, let's just take the nitric oxide one there. So let's do nitrogen dioxide. Remember, nitrogen dioxide is formed by lightning strikes with oxygen, forms nitrogen oxide, and that nitrous oxide reacts with oxygen to form nitrogen dioxide. It's also formed by catalytic reactions in cars, right? So there's nitrogen dioxide in the atmosphere. When it reaches the stratosphere, okay, that there can react with the radical. Now, it doesn't have to be this radical here, right? It can be radicals just from the normal production of ozone. So remember, in the previous section, we said that oxygen was homolytically broken down by incoming UV radiation to oxygen radicals. So it can be these oxygen radicals which react with the nitrogen dioxide. Okay, and when those react with the nitrogen dioxide, then you get a nitric oxide radical and oxygen. That nitric oxide radical can then react with the ozone. And then that's going to destroy the ozone. It's actually going to make nitrogen dioxide again, but then also oxygen. Now that's really interesting, because if we add these two reactions together, that cancels with that, that cancels with that. And what's the sum of these radical reactions? Right, O3 plus a radical to give 2O2, which is that. Okay, so that general reaction occurs either from the radicals reacting with ozone or via these other radicals. It's the same reaction, right? Just a few more bits and pieces going on there. So that's the natural destruction of ozone. Make sure you check out the next video, where we're going to be looking at how chlorofluorocarbons, CFCs, and halons can cause artificial or synthetic destruction of ozone, and that's what creates the ozone hole, or thinning of the ozone, which then lets in more UV, and then we've got a problem there with skin cancer rates, etc. So check out the next video. Hope that makes sense, and I'll see you then. All right, cheers.